As we've seen in the past, sometimes it's much easier to consider functions in polar coordinates instead of the standard Cartesian coordinates. This change of coordinate system can make certain calculus and understanding of a given area or region a lot simpler, or of a given function. And the same is true when we are integrating. And so we can want to do double integrals over polar regions now. And so what does a polar region look like? Well, remember our polar coordinates. We have x equals r cosine theta and y equals r sine theta, right? And so now when we're looking in two-dimensional space, we're looking at points classified as points r theta instead of points x, y, right? And so when we're looking at some region over in polar coordinates, we can start at some theta value, say theta equals alpha, and then we can keep going to theta equals beta, let's say. And then we can also have two different r bounds here. We could have like r equals a here, and then maybe out farther, we could have r equals b. And so now a polar region is this like trapezoidal region almost. It's kind of like a trapezoid, but the kind of the top and bottom, if you will, here are slightly curved, right? There's a little bit of curvature to them because this is a radius. And this is the region R that we want to define the integral over. So what we want is a definition for the double integral over a region R of f of r theta dA. This is what we're going to look to derive here. We're going to look to construct a rigorous definition for calculating an integral of a function in polar coordinates over a region expressed in polar coordinates. And so let's take a better look at this region here. So here we have an interval, like here's r equals a, here's r equals b, right? We have an interval in the r direction. We have an interval AB. And let's partition AB into m subintervals. And we'll index this by I. So we have like R1, R2, et cetera, all the way up to like RI, RI plus 1, et cetera, right? And so we get this partition kind of gives us slices of this region here. Maybe I'll draw some more. Okay, and then we also can partition our change or our theta interval, right? We have a theta interval going from alpha to beta, so we can partition the interval alpha beta, right? And it's not a perfectly flat interval now, it's kind of curved, if you will. We can partition this into like n sub intervals, right? And so we can have like theta 1 and theta 2 and et cetera, you know, up to theta I, and then theta I plus 1, and then et cetera. And so now we've kind of, with these two partitions in mind, let me keep our region in red here so we can keep track of it, because some of these lines are all over the place. So here's our region, right? And now with these partitions, we get these subregions, like these sub-trapezoids, right? That look similar to the big region. It's just a much smaller copy. So maybe I'll use blue here for like let's say this one is, and it looks rectangular, but it shouldn't be perfectly rectangular, right? Let's say this is our region Rij. And again, when we're defining the integral, we want the volume, right? What is the integral going to be? The integral is going to be, well, we have some polar region here, and then we have some function like z equals f of r theta. And so we have some function up here, right? And the integral should give us the volume under the surface, but above this region, right? And so whatever kind of the volume of this, where the top is the surface and the bottom is our region, this is what we want, right? The integral is going to be the volume. And so how would we define the volume here? Well, it's going to be the area of the region R times the height. I'll just say h here, right? And so what we need to do first is come up with a formula for the area of this region R. And we can find area of this region R by first finding the area of these Rij's, just like we did in the past, and then summing up their area, right? And so what is the area of Rij going to be? Well, let's look at now a subrectangle or a sub-region, which looks kind of like a trapezoid, right? This is going to be Rij. So this is, like in the picture, what I've drawn in blue. And maybe to keep it color coordinated, I can overlap this with blue. Okay. So now this is quite close to a trapezoid. And what is the area of a trapezoid, right? It's 1/2 times the, like 1/2 times one side, and then times the sum of the other two sides. And so what is this side here, right? Well, this is our change in R, because we're going from Ri minus 1, like say here, this is Ri minus 1, we're going to Ri. And so this is Ri minus 1 all over m, because we've partitioned this interval m times, right? And then this is the same, so this is delta R. And now what about the length of these sides here, these curved sides? So if you'll remember, just basic arc length is if you have a curve like here, and you want just like the length of this curve, well, it's the radius times the angle, right? And so the length here is going to be r theta. And so our length of the bottom curve is, well, this is Ri minus 1 times delta theta. And then the length of this top curve here is Ri delta theta, right? So this is like S equals, because that gives us the length of this curve here. If you just have like a circle and you're going from like, say, 0 to pi over 2, right? Then it's just the radius times the angle, and the angle is pi over 2. And so then the area of this Rij is going to be, well, using a formula for area of a trapezoid, we get 1/2 delta R, so this side here, times R I minus 1 delta theta plus Ri delta theta, right? This is the sum of the two curved edges here. And so we can write this a little differently. Let's define Rij star to be 1/2 Ri minus 1 delta theta plus Ri delta theta here. And so our formula for the area of Rij becomes which we'll call delta A, this becomes delta R times Rij star delta theta, right? Or, so here, my bad. No delta thetas here yet, right? We're just kind of redefining this radius. So this is Ri minus 1 plus Ri. And so you can pull out a delta theta from here and here. And once we define Rij like this, then our area is, I got a little ahead of myself, our area is then delta R times Rij star delta theta. And this gives us a formula for the area. And now we need the height, right? So this gives us the area of one of these sub rectangles here, the area of this base down here. And now we need the height of this really thin prism. And the height is going to be the value of like a test point, again, inside this region. And we already have an Rij star, right? Well, it's Ri minus 1 plus Ri over 1/2. So that's going to put us at a halfway point between these two, right? So this is Rij star. And then we can pick a point on this this radius, and we can pick the point Rij star theta ij star. And then we have a test point that we can use, and we can plug in f. The height here is going to be f of Rij star theta ij star, right? And so that means our volume, like the volume of just one of these smaller pieces here, like I have in blue, the volume of one of these smaller pieces, which we'll write as delta V, well, this is going to be delta A times the height, which the height was the function evaluated at this test point here, Rij star theta ij star. Then let's plug in what we have for delta A here. And so I'll just write I'll copy the F first, Rij star theta ij star, right? And then this is times delta A. So, and then I'll write the R first. So we have Rij star times delta R times delta theta. And so this is a formula for the volume of this small region, right? And so the volume of the whole region is approximately the finite sum, where we sum all of these subrectangles up. So from I equals 1 to m, j equals 1 to n of f of Ri star theta ij star Rij star dr d theta. And that means the volume is exactly the result of taking the limit as m and n tend to infinity. So we have the limit as m and n tend to infinity of the double sum I equals 1 to m, sum j equals 1 to n, f of Rij star theta ij star Rij star delta R delta theta. And so now this is our formula for volume below some surface and above a polar region. And now we can provide a definition. The double integral over the region R of f of R theta dA is equal to the double integral over the region R of, well, so let's say this is the limit as m and n go to infinity of the double sum I equals 1 to m, j equals 1 to n, f of Rij star theta ij star Rij star delta R delta theta. Sorry, that's delta theta there. And we can express this now as the double integral of r going from a to b and theta going from alpha to beta of f of r theta r dr d theta. When we take the limit of m and n as they go to infinity, well, this the sum of these f's become the sum of the integral. The sum of these r's just become r, and then delta r becomes dr, and delta theta becomes d theta. And so what's really important here is that in Cartesian, dA is equal to dx dy, but in polar, dA is equal to r dr d theta. It's not just dr d theta. You have this r here that you can't forget about, because you've seen in the construction here, this r is part of the area of this region now. So we have to include this in our integral. And so when we're setting up an integral in polar coordinates, when we see dA, we know this is r dr d theta and not just like dr d theta. And so this is really important that, and if like we're converting from, say we have an integral in rectangular coordinates and it's a lot easier in polar coordinates. So we convert to polar coordinates. Well, when we convert from dx dy, we've got to convert dx dy to r dr d theta. And so this gives us a nice definition of the double integral in polar coordinates. Now that we've seen that, let's do a handful of examples. And so the first example I want to do is just to get familiar with polar regions. So not even integration. So let's sketch the region R given by points r and theta such that r is between 1 and 3, and then theta is between 0 and pi, right? Okay, so what is our region R? Well, theta is between 0 and pi, so we know we're restricted to the upper half plane, right? And if we're restricted to the upper half plane, then we can look at what our r bounds are. So our lower bound is a circle of radius 1 because r equals 1. And then our outer bound is a circle of radius 3 because our outer bound is 3. And so this, it's like half an annulus or half a donut, if you will. This is our region R here. This is R, right? And like the equation for this line is like x squared plus y squared equals 1, and the equation for this line would be x squared plus y squared equals 9. But we know in polar coordinates these translate to r equals 1 and r equals 3 respectively. Okay, and so before we did any integration, I wanted to just give a quick example about, sketching regions and getting familiar with what they look like. So now let's do an actual integration example. Let's evaluate the double integral of r 3x dA over the region R, which is points r and theta, such that r is between 1 and 2, and theta is between 0 and pi. And so now we know what our region is, right? Now it's an annulus again, but it's radius 1 and radius 2 this time. And it's still the upper half plane because theta is between 0 and pi. And we want the integral over the region R of 3x dA. And so you can see this, as it's expressed, is in rectangular coordinates. And so we have to convert this to polar coordinates, right? And so the first step is to express the integral, at, let's say in polar coordinates. Okay, And so this is double integral. Well, r, we know our bounds, right? R goes from 1 to 2. Theta goes from 0 to pi. And then we have 3 times x. But remember, x is equal to r cosine theta in polar coordinates. So this is 3r cosine theta. And then dA is r dr d theta. And so this integral becomes integral from r equals 1 to 2, theta equals 0 to pi of 3r squared cosine theta dr d theta. And now this is the integral we need to set up, right? And you can see this integral is much easier than, imagine if we tried to solve this integral in rectangular coordinates. Well, our bounds, right, we would be bounded between the functions like y equals root 1 minus x squared and y equals root 4 minus x squared. And so like these would be just our bounds, right? And so like we would have to plug these in after integrating with respect to y, right? And that could get like incredibly, like you can get really difficult integrals once your bounds get pretty ugly like this in rectangular coordinates. And so here, this is very standard integration and the bounds are quite nice. So when we integrate with respect to r, theta is constant, right? So when we integrate with respect to r, cosine theta is constant, which means we don't have to worry about it. It's kind of along for the ride. And then so we have 3r squared. Well, when I integrate r squared, I get 1/3 r cubed. And so the 1/3 with the 3 will cancel. And this is going to become integral from pi equals 0, or integral from theta equals 0 to pi of r cubed cosine theta from 2 to 1 d theta. And now we plug in 2 and we plug in 1, we get theta equals 0 to pi. If we plug in 2, we're going to get 8 cosine theta. If we plug in 1, we'll get cosine theta d theta. So this is then 7 cosine theta. So if you'd like, I can pull the 7 out front. Integral from 0 to pi of cosine theta d theta, which is now a very simple integral, right? It's the integral. Once you integrate cosine, you get sine theta from 0 to pi, and this is 7 times sine of pi minus sine of 0, which is 0 minus 0, so this whole integral was just 0. Okay. But this is an idea of evaluating integrals in polar coordinates. First, you have to, if it's already in polar coordinates, then you just integrate, right? But if it's not, like here, it was in Cartesian or rectangular coordinates, you first have to express the integral, like every aspect of the integral in polar coordinates, right? You have to make sure the bounds, the integrand, and the differentials are all in polar coordinates. Otherwise, it won't make any sense. So now let's see here. Let's look at integrals over general polar regions. Right, and so now we may have a region that looks like we have some theta equals alpha and theta equals beta, something like this. But now our functions, or our r bounds can be functions of theta, right? So this could be r equals h1 of theta and r equals h2 of theta. And so here we have like a more generalized region, D, we'll call it, right? And so we handle these just like we handle generalized regions in Cartesian coordinates. We have a theorem here that the double integral of f of r theta, like r dr d theta, over some general region D is the same as the iterated integral from r goes from h1 of theta to h2 of theta, and then theta goes from alpha to beta of f of r theta r dr d theta. And so now, again, it's the same setup of an integral, but now your bounds for r are functions instead of just scalars, right? Instead of just fixed r values, they are actually functions of theta. And let's see an example of this now. It's also good practice for integration. Let's evaluate the double integral over the region R of r squared sine theta r dr d theta, where R is the region bounded by the polar axis and the curve r equals 1 plus cosine theta. Okay, and so here's like quickly a little picture of this. We're bounded by the polar axis and the curve r equals 1 plus cosine theta, which kind of spirals like this. And so we want the integral over this region where r equals 1 plus cosine theta. Okay. Now, we need to set this up using this theorem up here, right? And so what's our lower bound for the radius? Well, we can start at the origin. So we have a lower bound of 0 for r. So here's the bounds, right? And what's our outer bound? Well, our outer bound depends on what angle we're at, right? You can only go so far out. Like however far you can go out changes depending on your angle. So that means our radius is a function of theta, which is exactly the function that's describing this curve. And so that means our upper bound is 1 plus cosine theta. And now what about our bounds for theta, right? Well, we're bounded by the polar axis, and we think of the x-axis as the polar axis, which means we're in the upper half plane, so we're bounded for theta from 0 to pi. And this means then that the integral over this region r of r squared sine theta r dr d theta is equal to the double integral where r goes from 0 to 1 plus cosine theta, and theta goes from 0 to pi of r squared sine theta. So we can write this as r cubed now, right? Because r times r squared, r cubed sine theta, dr d theta. And because r has theta in its bound, we have to integrate r first, right? And so let's integrate r. Integral theta goes from 0 to pi. We integrate r first. We're going to get 1/4 r to the 4th sine theta from 0 to 1 plus cosine theta. All of this d theta. Integral theta equals 0 to pi. So if we plug in 1 plus cosine theta, well, I can plug the 1/4 out front here. So we're going to get 1 plus cosine theta to the 4th times sine theta d theta. And now we can use u substitution here, right? We can let u be 1 plus cosine theta. And so du will become negative sine theta d theta. And we substitute this in, right? We're going to get 1/4 integral, and I'll have u bounds now. U is going to go from something to something of u to the 4th. Well, I have sine theta d theta, but here du is negative sine theta d theta. So that means I have to pick up a negative, which I'll put all the way out front there, du. And then I need to check my bound. When theta is 0, u is 1 plus cosine of 0, which is 1. So our lower bound is 2. And then what's our upper bound? Is pi. So when theta is pi, u is 1 plus cosine of pi, which is -1. So that bound is actually 0. And then you see we can flip the integral here by removing the negative. So this is positive 1/4 integral from u equals 0 to 2 of u to the 4th du, which is 1/4 times 1/5 u to the 5th after integrating from 2 to 0, which is 1/20th over 2 to the 5th minus 0, and 2 to the 5th is 32. And so 32 over 20 simplifies to 8/5 because they both have a 4 in common. And so this is the idea of how we can integrate over a general region now, right, where you can have upper and lower bounds being functions for upper and lower bounds for r being functions of theta instead of just constant numbers. Okay. And so lastly, this is where I'd like to stop for this video. Lastly, I want to quickly give a definition for the area of a polar region. Again, just like we calculated area for rectangular and general regions, the area of a polar region is, and we'll say like A of r, is just the double integral over the region R of dA, which is the double integral over the region R of R dr d theta. And so you can think about, like, when we're calculating area, is you're just integrating the constant function 1. This is giving you area. And so this is where I would like to, this concludes our talk about double integrals, right? We've seen them now in Cartesian and polar coordinates, both in kind of standard and generalized regions. And now we're going to step into the realm of functions of 3 variables, and we'll try to analogously construct integration in 3 variables, which gives us triple integrals. And so we'll discuss triple integrals in Cartesian and then so-called cylindrical and spherical coordinates. So that's where we'll go from here.